I'm going to pass on to the next speaker, where I keep on misreading the title. It sounds like Finding Life Beyond HDF5, but it's actually Beyond Earth with HDF5.
Hi there, okay.
Yep.
And my slide showing?
Yep, looks good.
Okay, well, good afternoon, Europe, and good morning, America. Good evening, everywhere else. My name is Danny Price. I am the project scientist for Breakthrough Listen and a HDF5 proponent within our group. And today I'll be regaling you with our efforts toward the search for life beyond Earth and our data pipelines. So SETI talks often start with the slides, asking the question, are we alone? National Geographic back in 2019 kind of jumped the gun and put this on their cover saying we are not alone. And what they're getting at here is that the conversation has shifted somewhat in that we now know there's so many places where life could exist. The conditions for life we think are everywhere. The question is whether or not we can detect it. So most astronomers, most scientists think that life does exist beyond Earth. Whether or not we can detect intelligent life is another question, and the only way we'll possibly be able to answer that question is by doing a survey. So the galaxy, the universe, is a big place. This is the Hubble Ultra Deep Field. This is a section of the sky around a quarter of the size of the full moon. And there's around 300 billion stars, thereabouts, in the Milky Way galaxy. And most of these have a planetary system, and a good fraction of these have rocky planets upon which liquid water could exist. So the conditions for life as we know it exist. And there's trillions of galaxies in the universe, in the observable universe. And so if you take these two numbers and you times together, you can get an estimate for the number of stars in the universe and the number of places where we could look for life, and it's a big number. So how do we find life beyond Earth? And there's essentially three different methods that scientists are doing. The first one is you go there. So within the solar system, we can launch probes. Everyone probably knows about the NASA missions to Mars, Dragonfly missions of drones flying around the moons of Jupiter and Saturn. It's very exciting, but we can only hope to find microbial or some other life as we know it within the solar system. Another way that's going to come online in the next generation of optical telescopes is that they'll actually, with their spectrometers, be able to tell not only if a star has an exoplanet, but if that exoplanet has an atmosphere, and if it has an atmosphere, what the chemical composition is. So that's kind of amazing. They'll be able to tell that there's carbon dioxide and there's oxygen in amounts that you could only get with a chemical disequilibrium. So otherwise, it would be escaping off into space, and that suggests that something's creating this chemical disequilibrium from the geology on the planet. And so we may not know exactly what's causing it, but we could tell that there's something interesting going on that could be life. The other way that most people have probably heard of before is SETI, the search for extraterrestrial intelligence, which really is a technosignature search. It's a search for technology, for artificial signals in the sea of natural astrophysical processes. Now, the only issue with the NASA missions, and some people say these are the most likely to find life, given that we know it exists here on Earth, is that we can't really go beyond the solar system. So the number of planetary systems we can look at is one, at least for the near future. It's a little bit better with next generation telescopes, but those you still need to look for a very long time, and we're only going to be sensitive for the nearest handful of stars, so let's say 10. Technosignature detections, depending on how advanced the technology was, you could conceivably detect it from the other side of the universe, particularly for laser pulses, with the kind of technology we have in fusion labs here. If you connected that to a telescope, optical telescope, you could see that on the other side of the universe only for a nanosecond, but it would destroy a telescope, but you can do it. And with the technology we have in the radio spectrum, we could see across the galaxy. And obviously more advanced means that you can have stronger signals. Now the issue with two of these is that they're very expensive. Building stuff and going to space is incredibly expensive. Most SETI searches piggyback and use existing instruments. Just most telescopes are designed to do a wide variety of science, with SETI being just one of those. So they're comparably a lot cheaper in terms of the cost, but all of these are complementary and you don't just do one. We do think intelligent life is going to be less probable than microbial, but we need to look for all of them. So I work for Breakthrough Listen, and Breakthrough Listen is the largest ever scientific research program aimed at finding intelligent life beyond Earth. It was launched back in 2015 at the Royal Society in London with the late Stephen Hawking, Sir Lord Martin Rees, Frank Drake from the Drake equation fame, if you've ever heard of the Drake equation. He was the founder of SETI, essentially, and Andrew Yang, who was the director of Cosmos. The main funder there on the left, Yuri Milner. It's a 10-year, $100 million project, and we're about halfway through. My colleague likes to call this the Apollo program of SETI. So what we're doing, to give an overview, is looking at 1 million nearby stars. We're doing a survey of the galactic plane, which has roughly 10% of the stars in the Milky Way within it, and 100 galaxies, nearby galaxies. So these are looking at different distance scales, with nearby stars obviously being nearby, galaxies being much, much further away, but containing billions of stars. And the aim is to make all of our data open and all of our tools open source. The telescopes we've used in the first few years are the Parkes telescope, now called Murray-Yang, Indigenous Australian name, and the Green Bank, the Robert Seabird Green Bank telescope in West Virginia in the US. We've also been using the automated planet finder at Lick Observatory in California, which has a high resolution optical spectrograph one for looking for laser lines, whereas the other two are radio telescopes. And we're going to be bringing on the Meerkat telescope, and it's going to come offline very soon. And this is 64 dishes. It's a different kind of telescope where you combine all of these essentially sensors and combine them to act as one giant telescope. We also have a lot of partner facilities. LOFAR, Jodrell Bank, and NASA in Europe, the TESS satellite, the exoplanet survey satellite, and Gamma Ray is the FAST telescope. And so we're trying to get SETI done on a wide variety of telescopes and search as much of the electromagnetic spectrum as possible. So to kind of start the more technical side of the talk, we'll just start by talking about the observing we do and how we record data. So as you've guessed, we use a lot of computers. So the ones on the computers at Parkes on the left, and on the right is one of the 4 quadrants of the computers at Green Bank. These are ones that we were experimenting with liquid cooling, which was a lot of trouble and maybe more trouble than it was worth, but it did save some power at the expense of time. To give you an example of the data flow we have at Parkes, essentially we take the telescope, and one of the main things we're interested in is doing a survey of the radio spectrum, so forming a spectrum from the raw data and looking for artificial signals. So you have your signal up there on the top left. I've color coded it to follow the rest of the slide, and the telescope looks at a particular part in space. The electromagnetic waves come from outer space, hit the dish, get focused into the receiver, which sits at the top of the dish. The receiver then turns it into a signal and a coaxial cable. On the coaxial cable, that's connected to a digitizer, an analog to digital converter that takes that signal, turns it into ones and zeros. And this is where the computers come in. So we have a big network switch, which sends out a stream of UDP data from the FPGAs connected to the ADCs. So we have about 200 gigabit a second coming through for the Parkes telescope. It's higher for other telescopes. Meerkat will be 10, maybe even 30 times higher than this. And what we do is we kind of break it into sub-bands, so different frequency portions of the receiver's bandwidth. And it's about 8 gigabits per second going to each compute node. What we do is we capture them with the network card. They go into a ring buffer. From the ring buffer, they go into a GPU where we do most of our processing. And after that, they get written to disk. And they get written to disk. We can write the raw voltages to disk, the 8 gigabit second stream to our disks. We can keep up with that for up to 24 hours of the computers we have. Or we can write spectral data products. After that, and this is something that we generally do offline after we've done our observation, we can combine those subbands and transfer them to a data archive and reform the original spectrum. In terms of computers, this is what it looks like. We log in through a gateway to a head node, and that head node runs the file system for all of the other computers, like a HPC cluster. As of last month, we had about 13.6 petabytes of data on our disks. We've got 9 petabyte at Greenbank, about 3.5 petabyte at Parkes, and we've got around 5 petabytes of data that you can currently access via our Open Data Archive, which is hosted at Berkeley. So in terms of the data challenges, one of the main things when we were rolling up when we received the funding, we had to get things up on the telescope very quickly, and we weren't able to use distributed file systems in the time we had. And so we have the high-speed data capture and use direct IO to go directly to disk. So we just have a JBOD file system. We now have a newly commissioned cluster that we will be using for archiving at Berkeley. We have a lot of interest in the cloud, but it has remained too expensive because we work for universities. We don't have to pay as much of our power bill and as much of our networking bill. So we do get a good rate, but the cloud has steadily been improving in cost, particularly cold storage. When we started, 4 terabyte drives were all the rage, and now 16 terabyte drives are reasonably priced. So going into the HDF5 part is the storing and the analyzing of the data. So at the telescope, when we started, we wanted to use all the tools available from the Pulsar community, and they use a very simple format called SIGPROC filter bank. Essentially, it's just a header with the fields are there on the right, and then after the header, so you know your telescope's pointing, you have a blob of data, just a big binary blob of data. And the kind of data we have is essentially just a frequency, time, polarization, and dimensional array. It's not too structured, it's just a very big chunk of heavy data. This format was very simple to convert over to HDF5 because the data model was quite simple. So we can just take those header keywords and turn them into HDF5 attributes. We can take the data blob and turn it into a HDF5 data set. We do use compression on these data. The bit shuffle compression was originally made for radio astronomy, and so it's very good for the kind of data we have. We get good compression ratios. So that we can access both the filter bank and the HDF5 file, we have a Python package called Blimpy, and this makes a lot of use of H5Py and HDF5 plugin, which is has been much more reliable than for us for end users to install than BitShuffle has been, which requires a little bit more tech savviness. So one of the nice features that we found from moving to HDF5 is using virtual data sets. So we have data from Parkes, it creates 26 subbands, and that means 26 files per observation. And end users don't want to deal with 26 different files, and much prefer to just have one file. So the virtual data sets is something that we're very interested in using for our kind of next stage of data analysis, because it means that even though when we analyze the data, we may only be analyzing a little bit at a time, it is useful to be able to just treat it as one data, which is essentially what it is. As of last year, we got much more interested in the cloud. We had a fantastic group of students who made the BL at scale, and this is what we're using to prototype new machine learning algorithms and test cloud workflows, and we've learned a lot from that approach. And so we'd like to bring those techniques to our on-premises data archive and our computer cluster that's also at the data archive. So this is kind of the last slide, and this is there's a lot of open questions here, which perhaps people on the call will have some ideas for. We've recently rolled out Gluster. It was something that our sysadmin was decided was the best for our data, which is kind of a write once, read quite a lot of times, and it's quite a large, so it was better than Ceph and other options, and it was something he was comfortable rolling out as well. So we end up with Gluster. We also have a Jupyter Hub server, which we can use to serve notebooks on, and that's been very useful for getting a larger community of people to be able to analyze the data. What we would like is to write something so we can use the Jupyter Hub and spawn it across servers at different sites. No matter where the data is, you can open a notebook in the right place. One of the questions we have is what kind of tools can we use with Gluster, and what should our data analysis approach be? I guess the two things we have are the kind of cloud mentality versus the HPC mentality. So for HDF5, we can use Slurm and Singularity containers to provide something where our end users can use and run on our HPC nodes. which is one option, or we can try something perhaps with HSDS if we convert Blimpy IO methods library to use H5PyD. So that's essentially where we're at, what we're doing, and we've had HDF5 has been very useful for us, and we know that we haven't really started tapping all the more advanced features, which we're hoping to do in the coming years, because it really will just make it much easier for other scientists to do other science, and you get the maximum output from all of these telescopes. So thank you.
Thank you. Fascinating. Very nice talk, Danny. I used to be a radio astronomer, so some of this sounds familiar, which is very nice to hear.
Fantastic. Yeah.
Are there any questions? Anyone got their hand up? Or I had one which was about do you allow like on the open data? I haven't been to the portal, but do people download the HDF5 files, or do you leave them on the?
It's mainly been astronomers who have downloaded the data, and it's mainly been for other astronomy they want to do. This is an issue that I'm sure many people are familiar with. You can't download petabytes of data to your laptop, and so we want to have that cloud opportunity with the Jupyter Hub for people who just want to play around with the data and to be able to afford that. But we're also just trying to find the best ways when we do our massive data analysis, when we have a new algorithm or a new approach, to go through our data again. Maybe they're two different use cases, but they're the kinds of things we'd like to do.
There's I think Johnny already speaking later on, so I hope he will be able to give you some answers about H5PyD and also about HSDS and Gluster. I mean, I think there will be some. He's actually the next talk, isn't he? No, that's we first have Ellen. Yeah. So I think, Laurie, have you been catching up our time? If you don't have questions, we'll then move on and bring up your questions again during the discussion. Yeah.
Yep, we need to move on.
Okay. Thanks a lot again, Danny.